Hello, in this video I'm going to briefly run through 4 things that I get asked about a lot in tutorials when people first start studying quantum physics. I know I've got 3 things in the title, but I've just thought of a 4th one, so I'm going to include that. And these 4 things are Heisenberg's uncertainty principle, Pauli exclusion principle, quantum entanglement, and then atomic energy levels, which is the one that I've just thought of. And we've got the usual caveat here for this particular series of videos. We don't have the math skills yet to go into these in great detail. That'll all come if you go off to university in order to study physics. So I'm just going to give a brief overview of each one of these things, so at least you've got a flavour of what they're about. Because a lot of people hear of these things. They're very commonly used terms. So we might as well know a little bit about them just so we know what we're getting into when we study quantum physics in more detail. Right, so kicking off then with atomic energy levels, and there's something that's been hanging over us with the structure of an atom ever since we first learnt it, really. You know, this has all come off of the back of Rutherford, Geiger and Marsden, that alpha scattering experiment where they came up with the first model of the atom with this central nucleus, this small nucleus of positive charge at the center of the atom, and then electrons orbiting around the nucleus in these energy levels. And this has just sort of been hanging there, as I say, over us since this was first described to us and we first learnt it in our physics or chemistry lessons. Because we've got the 2 questions really that jump out immediately. Why do we have energy levels? And why don't the electrons, which are negatively charged, just fall into the nucleus, which is positively charged? It just doesn't really seem to make any sense. It makes even less sense when you're just looking at this from the point of view of classical physics, because if we've got an electron orbiting, so it's moving around in some kind of circle is how it's getting described, at least when we first come across this model of the atom. Well, if it's moving in a circle, it's constantly accelerating. If you've got an accelerating electric charge, then it's emitting electromagnetic radiation. This is what we're told in classical physics. So if this electron is constantly emitting photons, then it must be losing energy. So it would just spiral inwards until it reaches the nucleus, which isn't what happens. So we've got a lot of questions here that need to be answered. Now, I'm not going to be able to answer all of these in detail in this video, but at least we can start poking away at what these answers might be and where they might come from. You know, obviously the answers are coming from quantum physics. That's why I'm including it in this video. And it was Niels Bohr who first started dealing with this in 1913, so not long after Rutherford, Geiger and Marsden had done their experiment. And he suggested that the angular momentum of these electrons was quantized. Yeah, so he was still thinking, at least partly in a classical physics way, of talking about angular momentum of an electron actually orbiting round in these circular orbits. And he was saying, well, if the angular momentum is quantized and it's in multiples, he worked out that there'd be in multiples of the Planck constant divided by 2 pi. Then if this was a case, then they couldn't be radiating this energy and then spiraling into the nucleus, because then you'd have a continuous range of energy, so the continuous range of angular momentums. So that was his first explanation, which at least was a step in the right direction. You know, it matched well with observations he was looking at single electron systems, so systems that have got 1 electron in, so a hydrogen atom, a helium atom with, which has been ionized once, or a lithium atom which has been doubly ionized. So looking at those with single electron systems, and he noticed that this multiple here of the Planck constant divided by 2 pi, then that was describing where these energy levels are. Just a quick note on this as an actual constant. This comes up so often in quantum physics that is then given a new name. So we've got Planck constant divided by 2 pi is then called the reduced Planck constant. And that is just then referred to with the h for Planck constant with a bar through it. So it just saves us having to write out h over 2 pi every single time. So when you're looking at a lot of equations in quantum physics, you'll see this h bar turning up all over the place. It's just saving us having to write all of that out all of the time. So anyway, this made some good predictions anyway for where these energy levels actually are located. We don't describe atoms in this way anymore. Quantum physics is much more nuanced than this. It's much more sophisticated in its descriptions. And these energy levels are now based on wave theory. So the wave functions that I've mentioned in passing in previous videos, so wave functions associated with these electrons orbiting the nucleus, these then set up standing waves. So we're getting harmonics, essentially, which is why we're getting multiples of this reduced Planck constant. So you're getting standing waves of these wave functions. So they're like probability standing waves, really. And these probability standing waves, the nodes and antinodes, then match up with the energy levels and the gaps between the energy levels in the atoms. So yeah, a bit hand wavy there, but at least you can see something which is going to then be explained when you understand quantum physics in more detail at university. Now, another thing that actually features in the why isn't the electron just in the center of the atom, why doesn't it just combine with the nucleus, is then leading us on to Heisenberg's uncertainty principle, which loads of people have heard of. And this is saying that there is a limit in the precision with which certain pairs of physical properties can be known simultaneously. So most notably, the position of an object and the momentum of an object. So the more accurately one of those is measured, the less accurately the other one could be measured. There's some built-in uncertainty in these pair of values. This is not due to the accuracy of our measuring equipment. There is an actual built-in uncertainty. Now, at the macroscopic everyday scale, these uncertainties are negligible, but not at the microscopic level. At the microscopic level, when we're getting down into our quantum mechanics, this uncertainty that's built into these values really does matter. Now, Heisenberg himself, he gave an example of this. So say you were measuring the position and momentum of an electron. Well, you need a photon interacting with that electron in order to be able to measure this position and momentum. So a higher frequency photon will measure position more accurately than a low frequency one. So if we want to get really good measurement of our position, our X here, then we want to ramp up the frequency of the photon. But then if we got a higher frequency photon, it's got greater energy, and that greater energy causes a greater disturbance in the momentum. So we increase our accuracy of measuring position, but we decrease our accuracy of measuring momentum. So that's the example that Heisenberg gave on this. And then you get the way this is formulated in the mathematics is that our uncertainty in the position multiplied by the uncertainty in the momentum has to be greater than or equal to the reduced Planck constant divided by 2. So that's what the Heisenberg uncertainty principle is getting at. So if you've got something like an electron in an atom, and then, well, if you've got the electron actually sitting in the nucleus, if it actually moves too close to the nucleus, well, you're going to have a problem with Heisenberg's uncertainty principle as well. You're going to know too much about position and momentum, and that's another thing that's then going to break down. So we've got more things that are factoring into where electrons actually appear inside atoms. So that's the uncertainty principle. The exclusion principle, I've mentioned that quite a lot in the structure of matter videos. So this was laid out in 1925. So this is the Pauli exclusion principle. So Wolfgang Pauli, and he was looking at electrons initially, but this has been extended to all fermions. So remember, fermions, these are our leptons and baryons. So the leptons, so electrons, positrons, neutrinos associated with those, so the electron neutrino and the anti-electron neutrino. And baryons, so our protons, our neutrons, so things with odd numbers of quarks. These are particles with half integer spin. Spin's this term that we've been throwing around quite a lot. It's one of the things, one of the quantum properties of particles. So if you've got half integer spin, then any particle with half integer spin will obey the exclusion principle. What the exclusion principle is telling us is that two identical particles with half integer spin cannot simultaneously occupy the same quantum state within a system. And we represent this, probably the closest we get to looking at this before we go off to university, is when we're drawing out in chemistry, our up arrows and down arrows for our orbitals for electrons. So this is what it's getting at here. We've got two particles here, two electrons with half integer spin, one of them spinning up, the other one spinning down. So we've got plus a half and minus a half on these things, and they can't occupy the same quantum state within the system. So if we get another electron coming along, it can't go into this state. It has to then start filling up these energy levels, start filling up the orbitals. This is why fermions, essentially everyday matter, I included in that list of fermions everything that our everyday matter is made out of, protons, neutrons, electrons. Everything in everyday matter is stable and occupies volume because they fill up space. They can't occupy the same space because of this exclusion principle. So they start building up and building up. They're occupying volume. They're more stable from that point of view. You can't squeeze them too close together. So it's a combination of the exclusion principle and the just general structural robustness of matter that means stuff has volume and we get solid matter. So when I'm talking about the structural robustness of matter, so the strong nuclear force holding the nucleus of an atom together, the electromagnetic forces that are binding atoms and molecules together. So that's giving structure and robustness to the matter. So you need that. You need all of those forces, but you also need the exclusion principle to stop all of these particles just occupying the same space. So that is what is so important about the exclusion principle. Right, last up then, quantum entanglement. Right, this one might be the most difficult one to talk about with all of these. So this is where the quantum state of a particle. So when we're talking about quantum states, we're going through all of these properties of a particle which are quantized in some way. So you can have quantized, spin, charge, angular momentums, and all of these different things. So they get quantized, and you for a particular particle, you can list out all of these different quantum numbers, quantum states of these particles. With quantum entanglement, we've then got a pair or a group of entangled particles where the quantum state of each particle cannot be described independently of the quantum states of the other particles. So say we had some pair of particles here, just to keep it simple, a pair of entangled particles, and we want to actually list out, what are all of the quantum values, all these quantum states? What is the quantum state of this particle here on the left? Well, we can't give the quantum state of the particle on the left without reference also to the particle on the right. There is a correlation between the two of them. They are entangled. And this really bothered people when this was first discovered. Einstein famously was not happy with this. I mean, this is something that doesn't feature in classical physics at all. This is completely new to quantum physics. Einstein he described this as spooky action at a distance. And the reason he called this spooky action at a distance is, say you created this pair of entangled particles, and say you were just looking at spin, then you could create this pair, you could then separate them by a great distance. You could take them an enormous distance apart. Then you could start doing measurements on this particle here, this one on the left, try and find out what its spin is. Now remember, we've been talking about these particles as wave functions. So the spin of this particle isn't determined until we actually interrogate it in some way. So you interrogate it, you get a measurement for the value of the spin. That measurement then determines the spin of the other particle. And that feels like it's communicating then between these two particles that have been separated at great distance. And you've got this instantaneous transfer of information from one particle to another. That is how a lot of people viewed it at the time. It just didn't make sense. It seemed to be breaking too many laws of physics. Laws of relativity for a start. Einstein had been looking at that and saying, well, in relativity, you can't communicate, you can't pass information faster than the speed of light, and yet this seemed to be doing it. I mean, now people have got explanations for why that isn't the case, but back then you can see how it was bothering them. So one explanation that Einstein posited for this initially, and again, this has been shown to not be true, but this helps to clarify why this is so counterintuitive. Because Einstein was saying, well, what if? I mean, maybe the spin was already determined. This was his initial argument. He was saying, okay, you've created these two particles. You know one of them's got to be spin up, the other one's got to be spin down. Maybe it's just a case of, well, we don't know which one is which. So when we measure one of them, all we're doing is revealing already determined information. So if we found the one which is up, then the other one must be down. So that was what he was suggesting could be the case. It was like a local information, sort of hidden information that we're just then discovering. Now, this was shown to not be true in the 1960s. It was shown in the 1960s that these are genuinely undetermined until measured. So the one here on the left has still got a genuine 50-50 chance of actually being up or down. It's not just 50-50 of, well, is it up or down? It's not a straight probability in that point of view. Well, we've got one or the other. Let's just see which one it is. That isn't what it is. It is genuinely undetermined until measured. And then when measured, the other one has its value determined. But this is not, as has been shown more recently, in detail that, well, there's just no way I'm going to be able to get into it in this video, but it's something you will do if you study this at university. It's not transferring information faster than the speed of light. You can have correlated particles, these entangled particles, that aren't then communicating in that faster than light way. You can have correlation without communication. And this is something that you then work on, as I say, when you're studying quantum physics in more detail to see how that actually works and how these two entangled, or it could be, if it's a system, it could be more than two, this group of entangled particles are actually behaving as a single object. So that is it is an odd thing. I mean, it still seems, it's very hard to look at it as, when you're starting out, as anything other than just spooky action at a distance in the way that Einstein described it. But I think that's the way we get led to it, maybe, when we're thinking of these particles from a classical point of view, and we haven't had sufficient foundation in quantum physics, then it does look like magic. But once you start learning quantum physics in a more structured way, and you're doing that at university, you'll see that this does actually make a lot more sense, and there isn't anything spooky there. It isn't some kind of weird magic trick. It's just a different way of describing these objects as a correlated unit rather than as separate particles. So don't think, I think the key message of this is, when you're getting into quantum physics in more detail, don't think this is something mysterious, entanglement. It isn't something mysterious. So just go into it with an open mind, and you'll quite quickly see that this isn't anything spooky at all. It's just that people like Einstein back in the day, they didn't have the advantage of everything that's been learned since about quantum physics. So once you've learned those basics that he didn't have available to him back then, it won't seem spooky at all. Right, so that's four things then that come up a lot. Those energy levels, which have probably been bugging you for a number of years as to why we have energy levels and why the electrons don't just disappear into the nucleus. These three things then that you would have heard quite a lot about and possibly not known really what they mean, with the uncertainty principle, exclusion principle, and quantum entanglement. So hopefully that's unpicked a little bit about that, and maybe whetted your appetite to do more quantum physics modules, to pick those ones when you go off to university, because fascinating area of research. And how these things can be used, particularly if you're getting into computing as well. Quantum computing is such a big thing, of just seeing how we can utilize this new physics in order to get crazily productive computers with cut down on run times of analyzing big data and things like that. So there we go, fascinating area of physics.